So, coming to the conclusion of Riemann integrability, earlier we have discussed about the fundamental theorem. There it states that whenever you have an integrable function f on closed interval ab and phi is primitive of f, nothing but derivative of phi will give us f. Then if you want to calculate integral a to b f of x dx, then it will be equivalent to phi of b minus phi of a. Here one interesting thing is the importance of primitive here is nothing but to find the integration value of the function. So here we are not going to check the properties of the primitive. The only use of primitive is to evaluate the integral. So sometimes the primitive may be continuous or may not be continuous, but it is used to find the integration value. For example, I want to take one small example given in the book. Suppose you define the function f of x as 0 for x equal to 0 and 2x into sine 1 by x minus cos 1 by x for x not equal to 0. Now what happens if you define the function phi as 0 for x equal to 0 and x square into sine 1 by x for x not equal to 0. Now what happens if you consider the derivative of phi, it is nothing but f. Could you check on that? Derivative of phi is equivalent to f. Yes or no? Do you agree? Differentiation of phi using product rule x square and sine 1 by x. Right. So if you observe that you have done similar kind of problem in differentiability, that this function phi, is it continuous at x equal to 0? You can calculate the left limit as well as right limit. So the function is not continuous, but it is used to evaluate the integration of f. That was the thing I want to say here. If the function f is defined on closed interval something a say ab, which is involving 0, or if not closed interval say 0 comma 1, you define phi on the interval as like this, then phi dash equal to f, but it is not continuous. Clear? So but this function can be used to evaluate the integral 0 to 1 f of x dx. We can evaluate that. It is nothing but phi of 1 minus phi of 0. Is it clear for you? I am saying that if you want to calculate integral 0 to 1 f of x dx, it is nothing but phi of 1 minus phi of 0. That's it. But phi is not continuous at 0. Please understand that. It is not continuous. But we can use phi to evaluate the integral. So that thing we need to understand from the fundamental theorem. Okay? And it is to be understand that for each function we cannot find a primitive. Whenever primitive or antiderivative is there, in such cases we are going to make use of the fundamental theorem. If primitive does not exist, how we go on to evaluate the integration? There is a different issue. Okay, so the fundamental theorem is useful whenever primitive is existed. Even though primitive is not continuous, we can make use of the property. Clear to all? Any more doubts? Then I go to the other part, if you are clear. Fine. The other interesting thing is actually whenever we are going to evaluate integral a to b f of x dx, there is one small result that always this integral value is a multiple of b minus a. In other words, integral a to b f of x dx is nothing but some value into b minus a. It is evident from the mean value theorem, which is stated earlier, that this part is nothing but f of c, where c is a point lying between a and b. However, before this mean value theorem illustration, there is one small result that whenever you calculate the definite integral value, always its value is less than or equal to small m into b minus a and capital M into b minus a, where small m is the infimum of the function f and capital M is the supremum of the function f. So small m is equal to infimum f and capital M is equal to supremum f, and integration value will lie between these two. From this, it can be observed that always integration value is a multiple of b minus a. Some number into b minus a we are going to get. Okay? Is it clear to you all? So from this, I just want to state a small problem for you. I will left it as a practice, but I will give the whole illustration how to solve it. Just hold on a moment. I am going to take a problem on it. So before mean value theorem, the integration value is approximated like that. Note that whatever the properties you have learned at +2 level with regard to the integration, integral a to b f plus g is equal to integral a to b f plus integral a to b g. Similarly, the product rule, difference rule, division rule, whatever the properties you have learned at +2 level, for all these integration properties, you have the theoretical proofs with regard to Riemann integrability. Since these properties are out of the scope for our concentration, so we are not dealing with that. As and when you come across with Rirana's book under Rai Singhania or any other book, you can observe these properties with clear proofs. Why you are going to write this value is equal to sum of these two integrals. And integral a to b is nothing but integral a to c plus integral c to b. The splitting of integral we will do. How this comes? Is there any theoretical proof? So for each and every one, the properties which you have learned at integration at +2 level, for all of them you have the proofs with regard to integration and the Riemann integrability. But we are not studying with regard to the examination point of view, right? You please understand that. However, if you are interested, the proof is very clear and detailed. You can follow the standard textbook. But proofs are never given in the exams. Now, the problem I wish to take is root 3 by 8 is less than or equal to integral pi by 4 to pi by 3 sin x by x dx is less than or equal to root 2 by 6. Here I want to state one interesting that on observing this, whenever this is an inequality involving the integration symbol and the integrand contains two functions, what is the technique we go on to apply for proving this inequality? Can you say? First mean value theorem, right? Not mean value theorem, first mean value theorem, because it is involving two functions where the resulting condition is given as mu into integral a to b g of x dx. Here the integration is nothing but pi by 4 to pi by 3, the interval. So by applying that technique also you can prove this inequality. There is no doubt at all. Apart from this, I am giving the other technique which is useful to you. Because for solving a single problem, you have multiple methods are there. So here the function is nothing but f of x is equal to sin x by x. And how can we check that whether the function is increasing or decreasing? So I say that you can calculate f dash of x. So you are going to get the value as, after simplification I am writing the value x minus tan x of cos x by x square. So in the numerator, this part x is less than tan x in the given interval. So numerator is less than 0. So f dash of x is less than 0. I am giving the illustration how to solve the problem. You can solve it on your own. So since it is less than 0, the function is a decreasing one. So if you calculate infimum and supremum, infimum will be given by the upper point, supremum will be given by the lower point. So small m is equal to infimum f. This is equal to f of pi by 3. You substitute pi by 3 here. Capital M is equal to supremum f. This is equal to f of pi by 4. You calculate f of pi by 4 here. Now simply by substituting the values in the inequality, straight away you will get this answer. Now you can understand that this technique is very easy to prove the inequality, apart from using mean value theorem, also first mean value theorem. Because you are simply calculating infimum, supremum, substituting the values in this formula, and you are getting the answer straight away. Is it clear to you? Since the integrand is sin x by x, it has taken a little time for you by calculating f dash of x. Otherwise, if the function is very easy to check whether it is increasing or decreasing on the interval, straight away you can calculate infimum and supremum, and you can prove the inequality. That's it. Okay? Is it clear for you? The approach of the problem. Is anybody has any doubt with regard to the approach? Right. So this thing I want to share. Can I go for the other concept? Okay. Because I want to summarize the whole point of Riemann integrability. Because once we have finished it, we cannot come back. We are moving to the other chapters. So one other model is just hold on a moment. Suppose the problem is given like this. Evaluate the value of integral minus 1 to 1 f of x dx, where f of x is equal to mod x. So here the integrand is mod x. Not only mod x, you can take any other function which is involving modulus of x. So how to evaluate this? Now here we have one interesting property with regard to Riemann integration. In other words, we have another definition with regard to Riemann integration. So far we have considered that if you want to prove the Riemann integration concept, we are going to make use of the 5 things: continuity, monotone function, finite discontinuities, infinite discontinuities having a limit point for them, and UPF, LPF, if you calculate the difference between them, UPF minus LPF less than epsilon. These are the results which are useful to calculate the Riemann integration. And also, while solving the problems, the so far technique, what we do is we calculate lower integral as well as upper integral, and we will check whether they are equal or not. In that case, we are going to calculate UPF as well as LPF, and we are going to apply limit n tends to infinity to get lower integral as well as upper integral. For some particular case of problems, for finding lower integral and upper integral, straight away we will do the integration by taking infimum and supremum. If you integrate supremum, it is upper integral. If you integrate infimum, it is lower integral. So far, this is nothing but our problem solving strategies with regard to Riemann integration. All of you accept for it? Okay. Right. Now the another thing is, the same definition will be conveyed as integral a to b f of x dx is nothing but limit norm p tends to 0 summation r equal to 1 to n f of tr into delta r, where tr is any point in the interval, that is nothing but IR. This is another definition. Please take a note of this definition. You consider a partition, you take R subinterval, then as we know that integration is nothing but sum of the values. So integral a to b f of x dx is equal to limit norm p tends to 0 summation r equal to 1 to n f of tr delta r. The point tr is taken in the rth subinterval, delta r is length of the interval, and the limit norm p tends to 0. You have taken the maximum possible partition. Since norm p tends to 0 is nothing but limit n tends to infinity, this definition is equivalent to limit n tends to infinity, the summation what you consider f of tr into delta r. So apart from calculating lower integral, upper integral, and calculating the limits for them for UPF and LPF, this is the other technique to prove that integral a to b f of x dx is equal to what? Okay. So whenever the function involves modulus, we are going to make use of this technique. So we will use this formula to calculate integral a to b f of x dx. Please understand, here we are not calculating UPF and LPF. Simply for the sum, we are applying the limit. Okay. Is it clear for you? All of you. Right. Now, let us go into the problem. First of all, we take the function here, which is nothing but mod x. As we know the definition of mod x, it was defined as minus x and x for x less than 0 and greater than or equal to 0, its value is nothing but x. It was defined like it. You can say like this also. That is also correct. Now what happens while taking the partition on the interval -1 to 1 at the point 0, in this segment function is minus x, in this segment function is x. If the function value do not change over the entire interval, we simply bifurcate the interval into n parts. B minus a by n, usually we take delta r like that. So here what happens, we are going to make this part into n equal segments and this part into n equal segments. So if you apply delta r, we are going to take like this as so we should be cautious in choosing that delta r is equal to 1 by n. So how many number of intervals you are taking? N segments, 2n segments, 3n segments. Depending upon the interval, when mod x is considered, we should take care of it. Is it clear for you what I am talking? So the partition will be written like this. -1 is equal to x naught, x1, x2, so on. Xn is equal to 0, xn plus 1, xn plus 2, so on. X2n is equal to 1. In this way, we take the partition. Total 2n equal segments we have considered. So, if you write xr or tr, whatever it is nothing but -1 plus r by n, where r varies from 0 to so on, up to 2n. Or r is equal to 1, 2, so on, up to 2n. If you substitute these values, you are going to get the respective points. x0, x1, x2, x3, so on. Actually, we calculate delta r as b minus a by n, nothing but range is bifurcated into n equal segments, isn't it? Why we are making n equal segments? If you consider the graph is throughout varying in this way, the function is not at all changing. So from this part to this part, you are making n equal parts. Now here what happens, the function value is changing. Let me say if the function is 2x plus 1, throughout the interval its value is nothing but 2x plus 1. Here what happens, for half part of the interval its value is minus x, for the rest of the part its value is x. Did you get the logic? The function value is changing. In other words, we are integrating the two functions. That is why from -1 to 0, n segments I have considered. From 0 to 1, I have taken another n segments, total 2n segments. That was the idea. Fine. Otherwise, always for every problem, we take only n segments. Because the function value is changing here. For half of the part, its value is minus x. For the other part, its value is x. The function is changing. We are not integrating a single function. In other words, if you apply the formula of summation, we are taking the sum of two different functions. Half part, one function minus x. For the other half part, another function x. There is a small difference here. Agreed? Right. So this is the way in taking the partition. This is delta r. The point xr is written like this, -1 plus r by n. Why not? Partition belong to the total interval. Partition belong to the total interval. That's why earlier you can see the problem that integral a to b is nothing but integral a to c plus integral c to b. You have a property in integrations, right? Critical proof. Like that. There is no difference in making a partition. But for the same problem, you fix n only. There is no doubt at all. If you have a confusion why 2n is there, you can take like this as delta r is equal to 2 by n. 1 minus of 1. This is 2 by n. No change at all. But while calculating the sum, you have a doubt. Because for first n by 2 values, the function is minus x. For the remaining n by 2 to n values, its value is x. That also you can do. No change at all. In that way also you can do the problem. Since always we are making n equal segments, to follow the tradition I have done like this. For simplification part, exactly. To avoid confusion in the simplification. Because, let me say, if we have taken only n parts, as per the definition I have mentioned, integral minus 1 to 1 mod x dx is equal to limit n tends to infinity summation r is equal to 1 to n f of xr into delta r. Accepted? Yes or no? The formula I have given earlier. Now what happens? For the first n by 2 segments, its value is minus x. For the half, its value is x. Now what happens? You are going to apply this as limit n tends to infinity summation r is equal to 1 to n by 2 f of xr delta r plus summation r is equal to n by 2 plus 1 to n f of xr delta r. Because here the function value is minus x, here the function value is x. It is changing. Accepted. So, while simplifying the term, you will have a little confusion and doubt how to simplify the part. To avoid that, I am taking this is n parts and this is n parts, total 2 n parts. That was the whole idea. Okay? Any more doubt for anyone? Right. So, coming to this part, so I have taken 2n segments. R is equal to 1 to 2n. So limit n tends to infinity summation r is equal to 1 to n f of xr into delta r plus summation r is equal to n plus 1 to 2n f of xr into delta r. In this way I have bifurcated. So this is equal to limit n tends to infinity summation r is equal to 1 to n. See, I have written xr as minus 1 plus r by n. So this is nothing but f of minus 1 plus r by n, and delta r value is nothing but 1 by n. There also we have the same property. And how the function is defined? For the first n parts, it is minus x. For the other, it is x. So how it is going to be varied? Summation r is equal to 1 to n minus of minus 1 plus r by n into 1 by n plus summation r is equal to n plus 1 to 2n minus 1 plus r by n into 1 by n. The rest of the part is nothing but simply applying the limit, you will get the value. The value is nothing but 2. If you simplify the total value, the value you are going to get it as 1. For the first one, you will get the value as minus 1 by 2. For the other one, you will get the value as 3 by 2. So the value is 1. It is just like applying sum of the first n natural numbers simplification. Nothing else is there. This part you have done already in previous problems. After calculating UPF and LPF, you will do that. If you have a doubt, I will simplify this part also. You please tell. As per our convenience, I will go. Applying summation to minus 1 and r by n separately, and we will calculate the limit part. If anybody has any doubts, you can ask. Is it required for you? If so, I will go. Right. So in this way, we will solve the problem involving negative value to positive value and a function having mod x. Let me say one simple problem, that suppose the problem is given as integral minus 2 to 1 mod x dx. Now can you tell how many parts you are going to take here? N intervals, 2n intervals, or 3n intervals? if your problem is given as integral minus 2 to 1 mod x dx. You can take 3n, because see, the technique here is we should get delta r is equal to 1 by n, because as n tends to infinity, 1 by n tends to 0. So always we should have delta r is equal to 1 by n. That is the underlying idea. So if you take the range 1 minus of minus 2, 3. So if you take 3 by 3n, then you will get 1 by n. So we'll take 3n parts apart from 2n parts. You can take 2n also, because if you take that 3 by 2n, so delta r is nothing but 3 by 2n. You may have little difficulty in the simplification part while applying sigma. Otherwise, there is no doubt at all. There is nothing wrong in taking 2n intervals. For computational convenience, we take 3n. That was the only idea. So this kind of problem you can expect in UPSC. I think this kind of model earlier is given. Any more doubts overall this approach of the problem to anyone? Right. So at this point, I want to conclude my discussion. Sorry, I just want to take one more small concept, very simple concept. Then I will conclude my discussion on Riemann integrability, and I will start improper integrals. Because I am going to take each and every problem solving concept. Later, while reading the standard textbook, you can come across with the examples, you solve them. And as and when you have a doubt with regard to the solution part, I will take a doubt clarifying session separately on Riemann integrability. Because with regard to exam point of view, it is most important, the Riemann integration. The other part I want to take, that is, suppose you take f of x is equal to step function of x, the integer part of x, on the interval 0, 4. And you are going to find the value of integral 0 to 4 step function of x dx and what it will be. So on the whole, if you observe the pattern of problems involving modulus of x, problems involving integer part of x, problems involving mean value theorem, integral as a limit of sum, problems involving first mean value theorem and fundamental theorem of calculus, and UPF, LPF applying limit. This is the whole idea of problem solving strategies in Riemann integrability. Okay, this is the last resort. So you can take x into step function of x, only step function of x, anything you can take. So integral 0 to 4 step function of x dx is given. Now the first question arises is, the function step function of x, is it integrable or not? The first question. If it is integrable, then you are going to integrate it. If it is not integrable, integration cannot exist, right? So here it is given that what are the value of integral. So let us assume that it is integrable. So what are the source of, or what are the source we have that it is integrable? Can you tell? Depending upon the fundamental results we have discussed earlier. How can we identically say that step function of x is integrable? Yes, not limited discontinuities, finite number of discontinuities. If you have used the word limited discontinuities, means discontinuities are so many having limit point. We should take the other word. But your verbatim is correct, your sense is correct. Number of discontinuities are limited. In that way you have said, right? Yeah. So here, if you observe discontinuities, what are the discontinuities here? 1, 2, 3, 4. These are the discontinuities. Accepted? Right. So if you elaborate the function value, how it is going to be? The function of x is nothing but 0. if you take x from 0 to 1, its value is 1 from 1 up to 2. Its value is 2 from 2 up to 3. Its value is 3 from 3 up to 4. Accepted? I think this definition you have known, that integer part of a function. All of you, I think so. Is it known to you or not? Right. So in solution part, how do we mention, since integer part of x having finite number of discontinuities 1, 2, 3, 4, it is Riemann integrable by a known result, and the function value is nothing but 0, 1, 2, 3 under these segments. Now straight away we will integrate. So integral 0 to 4 step function of x dx is nothing but integral 0 to 1 step function of x dx plus integral 1 to 2 plus integral 2 to 3 plus integral 3 to 4. So it is nothing but integral 0 to 1 0, integral 1 to 2 1, integral 2 to 3 2, integral 3 to 4 3. Simply doing integration you will get the answer. I think you know how to integrate. That's why I'm lefting that part. So if you simply integrate and applying the limits, its value is nothing but 6. 0 dx, 1 dx, 2 dx, 3 dx. Simply doing integration. You just check on that. So here the value is 0 dx, here 1 dx, here 2 dx, here 3 dx. Derivation integration gets cancelled, apply the limits, you will get the answer at 6. You can check on that. By fundamental theorem, if you say, there is no need to mention fundamental theorem here, as and when bifurcation is done, straight away we will do the integration. That's all. So fundamental theorem will be used if we say that it is primitive of f. Now there is a question arises for us, what is the primitive of f here? The step function of x. So we should not complicate ourselves. So the thing here is, the only ideology before us is how to solve a problem, not how to make use of this theorem. You can apply any kind of strategy. That's why, apart from using first mean value theorem, I have given an inequality earlier, m into b minus a. That is very useful in solving the problem, apart from doing that big first mean value theorem. But that theorem is very profound in solving so many problems. But some problems will be easily solvable by using this kind of inequalities. Here also, by simply doing integration, you will get the answer. So on the whole, I have covered all type of problem methodologies in solving them with regard to Riemann integrability. So I want to conclude my discussion here on this integrability chapter, and let us move with improper integrals. It is simply problem solving session which will be useful to you. Maybe some of you have come across earlier. For them it will be a just refreshing session. For the others it will be very interesting for you, because it is just problem solving techniques, not more than that. So if you confirm yourselves, then I will start with the new chapter. And I will say my simple suggestion to all you is, please go with either Reanalysis by Rai Singhania or Krishna series, whatever the book you are following. Just read this chapter Riemann integrability one more time, because apart from having class session, seeing the examples in those books will be very helpful to you, and you will get the glimpse of Riemann integrability, how interesting it is, so that you will get different ideas while solving the problems. My advice is, there is no need to go with the exercises, because majority of the questions under UPSC are coming from the examples itself. Occasionally you can expect 1 or 2 questions from exercise part. And can I ask you one question, that what about the previous math optional paper? I think some of you have applied for it, attempted, or your friends may attempted that. Any comments on that paper with the level of UPSC? And if some of you have attempted test series from our institute, what is your comment on that with regard to paper 1 and paper 2 of UPSC conducted in this month? paper 1 is easy, paper 2 is moderate. Okay. Anything to add? Fine. That I agree, because the questions which we have given in test series, I think at least 5 to 6 questions have come in those papers with regard to paper 1 and paper 2. And paper 1 is easy, paper 2 is moderate. And one interesting thing is, some of the previous questions are repeated here. That is the interesting thing to observe. In one sense, we can feel that if we limit our preparation to certain aspects, definitely as per such kind of papers, you will get good score. That is my conclusion on the whole. Yes. Yes. The same sum I have given in test series, and it is taken from the previous year papers also. It was repeated under Riemann integrability. That's why I said. And these sums, majority of them are examples taken from different textbooks. Please understand, because the syllabus is vast. For some particular topics, you need to prepare the textbook as well as the exercises too. For some chapters like analysis and others, I will inform later, examples are enough. There is no need to go much deeper. That's the advantage of math optional. Thank you. So let us begin our new chapter, that is improper integrals. So let us take the integral a to b f of x dx. So just forget about the whole thing of Riemann integrability. We are not at all using that chapter here. You forget about limits, continuity, differentiability, integrability, everything you forget. We are simply learning a new chapter. It is just like calculus, improper integrals, right? So when do we say that this is a proper integral, or how do we say that it is a proper integral? Can you say your views? Infinite, improper. I will give some of the things, right? Is it a proper integral or improper integral? And I will give one more example. Did you come across this kind of problems at calculus or +2 level integrations? Are you getting any idea the definition of proper integral or improper integral? Now let me give. We say that the integral is proper if it is satisfying two properties. The first one is the interval what you are taking must be finite. So generally while doing integrations, we never consider this type of thing. It is an infinite interval, right? Isn't it? So the first thing is we always take the finite interval. Second one is the function what you are taking, it must be a bounded, because the whole of Riemann integrability we have learned that integration should exist for the bounded function. I mean, in order to evaluate the integration of a function f must be bounded. These two things. So whenever f is a bounded function and the interval is finite, integral a to b f of x dx, we call it as a proper integral. If one of these conditions or both are not satisfied, we call it as an improper integral. Can you recollect this definition? Is it that known to you? Or not known to you? Please give your responses. And you can correct me if I go wrong. Is this concept known to you or learning for the first time? Right. So you take the thing that the interval AB is finite and f of x value should exist on the interval. That means f of x should not be undefined at any point in this interval. If these two are satisfied, we say that this type of integral is a proper integral. The simple example is integral 0 to 1 x square dx. The interval is finite and x square value you can find at each and every point over this interval. Accepted? So that is a proper integral. Now see, if you observe this thing, even though the interval seems to be finite, 1 by x is undefined at the point 0. So this is improper integral. Here the interval is not finite. Here also the interval is not finite. So the whole summary of this chapter is nothing but whenever an improper integral of this type is given to you, how to find its integral value. That's it. What is the formula and what technique you are using. There is no theory at all. Theory is there, but you are not learning the theory. We are just learning the formula, how to solve a problem. That's it. It is just like doing integration one more time. Okay, that's why it will be very interesting to all. So in the conclusion, what is an improper integral? First part, the interval is not finite. Second, the function has discontinuities. It means the function is going to be undefined at some of the values in the interval. Third, both having infinite values and interval is not finite. These three criteria, whenever an integral is having, it is called improper integral. Okay. Now, on observing this pattern, it was mainly classified into three types. The improper integral is mainly classified into three types. First kind, second kind, third kind. So what is meant by first kind? So in this, we say that the improper integral having one of the limits or both the limits are undefined. So in integral a to b, either a is undefined, say minus infinity, or b is undefined, infinity, or both are undefined, minus infinity to infinity. That is called first kind. So the second kind is given by interval is finite, function unbounded. Means at some of the points in the interval, you are getting f of x is equal to infinity, undefined value. And the third kind is nothing but 2. interval is not finite, function is also unbounded. So the entire classification of improper integrals come under three categories: first kind, second kind, third kind. First kind means in which interval endpoints are undefined, infinity, either both or one endpoint. In the second kind, interval is finite, just like 0 to 1, 2 to 3, 1 to 4, etc., etc. But the function is giving undefined values at some points. And third kind is both. Interval is undefined, I mean not finite, function is also undefined. Clear? So let us go with the first kind, and how to solve such kind of problems we go on to discuss. Shall I continue? Is that concept clear for everyone? What we are going to do actually in this chapter? Fine. So here we are not learning any separate theory. We are just doing integration by some sort of concept. Suppose you take the first kind integration, improper integration. So suppose it is of the form integral a to infinity f of x dx. Now how to solve it? It is very simple. So where t is greater than a, let me see. So you take that if upper limit is infinity, you will write this integral as limit t tends to infinity integral a to t f of x dx. So evaluate this integral first. For the result, apply limit t tends to infinity. If the value is finite, the same value is applicable for this one. If the value is not finite, this integral is divergent. Its value is not finite. Clear? Take a note of that formula. Similarly, if you have the part like this, integral minus infinity to b f of x dx, what you are going to do? You are going to do limit t tends to minus infinity integral t to b f of x dx. We do the same thing here, where t is less than b here. And what happens if integral minus infinity to infinity f of x dx is there? So we simply split like this. Where a is any point between them, and we do the previous two procedures for these two. That's it. Please take a note of that. After noting, please inform. Shall I erase this formula? Fine. All of you. Right. It is just doing your integration problems one more time. That's it. The only modification is we are simply applying limit. That's all. Suppose it is given that take this problem once, and another one for our convenience. Let us take these two problems one more time. So it is nothing but limit t tends to infinity integral 1 to t 1 by root x dx. Can you say what the integration value of 1 by root x? It is x power minus 1 by 2. So x power minus 1 by 2 plus 1 by minus 1 by 2 plus 1. So 2 root x. Am I correct? The integration. So this is equivalent to limit t tends to infinity 2 root x between the limits 1 to t. So if you apply the limits, so what will be its value? Is it finite or infinite? Please tell. Are you getting the idea what I am doing actually? Right. So if you apply t tends to infinity, what is this value? Is it infinite or finite? Infinite. So this value is infinite. So integral 1 to infinity 1 by root s dx is also infinite. That is the solution. The integral is divergent in the other way you can say. So for this problem also we do the same thing. Is equal to limit t tends to infinity integral 0 to t dx by 1 plus x square. So what is the integration here? Is that tan inverse x, right? So equal to limit t tends to infinity tan inverse x between the limits 0 to t. So nothing but limit t tends to infinity tan inverse t minus tan inverse 0. So this is equal to tan inverse infinity minus tan inverse 0 is nothing but 0. And when do we get tan inverse infinity? It will be pi by 2. Accepted? Please check on the process what I did. Right. So is pi by 2 a finite value or infinite value? So it's finite, hence the solution is also finite. So this is the way in solving the problems. Let us take some of these problems also, which gives the idea. However, it is nothing but doing basic integration one more time. There are some complicated problems. For them, it takes a little time to do the integration. However, we apply the same integration techniques of plus 2 level here. So one problem I want to take is, let us say integral root 2 to infinity dx by x into root x square minus 1. Another one is integral 2 to infinity 2x square by x power 4 minus 1. Let us consider these two problems once. So again, this is improper integral. If you consider that it is equal to limit t tends to infinity integral root 2 to t dx by x into root of x square minus 1. Now the question is how to evaluate that integral. Any guesses from anyone? Say, can you recollect any formula for that? I think it will be secant inverse x. If you have remembered the formula, I hope so. So this is equal to limit t tends to infinity secant inverse x between root 2 to t. So this equals to limit t tends to infinity secant inverse t minus secant inverse root 2. So if you apply the limit, you are going to get the value as pi by 4. Pi by 2 minus pi by 4, the result is pi by 4. So just try to take a copy of the all previous year integration formulas of calculus. That is enough for you in solving this kind of things. For this chapter exclusively. So can you recollect that formula secant inverse x? Am I correct in giving that? Right? So since the value pi by 4 is finite, integral root 2 to infinity dx by x into root of x square minus 1 is nothing but pi by 4. That is the solution. Now let us take this problem. Now how to do this? So here we are going to do like this: limit t tends to infinity, integral 2 to t. So here I will write it as x square plus x square minus 1 plus 1 by x square minus 1 into x square plus 1. Yes, because this kind of stuff you have done earlier. So I will make space here. This equals to limit t tends to infinity, integral 2 to t, x square minus 1 by x square minus 1 into x square plus 1 plus x square plus 1 by x square minus 1 into x square plus 1 of dx. And individually we are considering the integrals. Now we have to take the values of them. So for this, the integration value is tan inverse x between the limits 2 to t, and limit t tends to infinity is there. And for this, I think the formula will be one by t into log of x minus 1 by x plus 1. Can you recollect that formula? It is simply based on intermediate integration formula. That's it. Nothing else is there. So this chapter is very comfortable and easy to solve. And obviously earlier, if you look at 2015, 2016 papers, obviously one question is given for 10 marks from this chapter. Occasionally 15 marks weightage is also there under improper integrals case. So whoever are fond of calculus, they love this chapter. Right? So can you apply the limit and give me the answer? I will say that you are going to get the value as 1 by 2 log 1 plus pi by 2 plus 1 by 2 log 3 minus tan inverse 2. Since it is a finite value, the given integral is convergent. Its value is nothing but the value you have obtained. And 1 by 2 log 1, since log 1 is 0, this value is nothing but 0. So pi by 2 plus 1 by 2 log 3 minus tan inverse 2 will be the answer here. I think you can apply the limit. That's why I have skipped that part. Is it required for you applying the limit? One thing you need to understand, while applying the limits, you can make use of the limit properties. Taking L'Hospital rule, if it is in the undefined form, you can apply L'Hospital rule also in applying the limits. So here, if we apply the limits here, log of 2 minus 1 by 2 plus 1, so log 1 by 3 will get. Applying t, log of t minus 1 by t plus 1, you take t common here, and then you apply limit t tends to infinity, because 1 by t tends to 0. As t tends to infinity, 1 by t tends to 0. In that way you apply the limit. Okay. In such case, you will get log 1. So if you are finished with this problem, then I will take the other. After finishing, you please inform. Right. So at the end, I will give some problems as a practice for you over these chapters. So one problem is, let us take integral 0 to infinity x into e power minus x square dx, integral 0 to infinity x cube into e power minus x square dx, and one problem you can take integral 2 to infinity dx by x log x, and integral 0 to infinity e power minus ax into cos bx dx. Let us take these problems. Later we will meet to some complicated things. So if you are doing them simultaneously, I will give the hint. Can you try on your own right now? I think that will be interesting. So I can observe that you are moving at the same pace like me in getting the concept. So for the first one, it is nothing but limit t tends to infinity integral 0 to t x into e power minus x square dx. And how we are doing it? Let us take that x square equal to z. So 2x dx is equal to dz, and you can vary the limits here. So how the limits will go on to vary here? Since x is varying from 0 to t, you have to take the same things. Or you can apply integration by parts thing also. So this implies x dx is equal to if x is 0, z is 0. If x is t, z is equal to t square. This is one way of solving that. Otherwise, you can do integration by parts also. That is also acceptable. So if you want to do integration by parts, it will be limit t tends to infinity. So use the formula ILATE, arithmetic, trigonometric, exponential. So e power minus x square Are you getting the idea here in solving it? So if you apply the technique, on applying the limit, you will get the value as 1 by 2. Please check on that. So 1 by 2 into upper limit minus lower limit, if you apply, minus 1 by 2 into 0 minus 1 you will get. I will say you are going to get the value as limit t tends to infinity minus 1 by 2 into this was the value you are going to get. Please check. So if you are finished with this one, here for this problem, limit t tends to infinity, you will take log x equal to z, 1 by x dx equal to dz. So integral 2 to t, however you will write the problem, dx by x log x limit t tends to infinity. So you have to take a log x equal to z, you will take the respective limits. You will take log x between 2 to t. The value will be undefined. So log infinity minus log 2, you will get infinity. So the given integral will be divergent. And for the third one, you have a formula. So the formula will be like this. You are going to get it as integral e power ax into cos bx is equal to e power ax by a square plus b square into a cos bx plus b sin bx. You can make use of this formula for the third problem. Integral 0 to infinity e power minus ax into cos bx dx. Okay, and you will get the value as, I will give the solution for you. You are going to get the value as 1 by a square plus b square into, say, 0 plus a, nothing but a by a square plus b square, which is a finite quantity, hence the given integral is convergent. So you please try them on your own right now. If you have a confusion, I will deal them one more time. I will wait for you, take your own time and solve them now. Then in tomorrow's session, we will take the different interesting problems on improper integrals. After finishing them, you will tell me. And that's all for today's session. So for the upcoming sessions, please take a copy from the internet. I hope so. You have a lot of problems and formulas available with regard to integration. Not all of them you require, some of them you require, not all. Some basic integration formula you require, some strategies in solving them, not all together. Because you can hardly find around 5 to 6 pages of formulae, which we will never use. At the most, 1.5 page formula we will use while solving these things. So that's all for today. Can I close our today's session? Or if you want to add something, you can add. Answer for last question, a by a square plus b square, because if you apply, the thing is going to come as, so limit t tends to infinity, the problem. So here you are going to get it as e power minus at into, because e power minus ax we have taken, between the limits, one limit is t, another limit is this number. So while applying t tends to infinity, since e power minus at is there, 0 into some finite quantity you will get, and the last you will get a, because it is 0. I hope so. Is it 0 or 1? Can you say? That's it. And 1 by a square plus b square will be there. It is a constant. E power minus at is there. So while applying the limits, this also will participate here. E power minus a infinity and e power minus a into that constant. So the last value will be a. The first part will be 0. So upper limit value will be 0. Lower limit value will be a. That's it. Okay. That's why a by a square plus b square you will get, which is a finite value. That is the solution of the given integral. So thanks to you all. We will meet tomorrow.